All right, let's look at these three problems and calculate what's called the crystal field stabilization energy or ligand field stabilization energy. And let's sketch it out down here at the bottom first. So what happens is when we have just the free ion, all 5d orbitals have the same energy. However, once we put it into an octahedral crystal field, the d orbitals split into the EG set and the T2G set. And in this process, what happens is the three orbitals go down, they decrease in energy by minus 2/5 delta oct. And the two orbitals go up by 3/5 delta oct. And so using this and then populating these orbitals, we can calculate something called the crystal field stabilization energy. That gives us some sense of how happy the free ion is to be in a crystal field. And so if we put tons of electrons down here at the bottom, it's more stable than the free ion. But once we start populating up here at the top, it can become equally stable to the free ion. It actually never becomes positive. All these values end up being negative or zero. So here's what you'll want to do in this process. So look at the complex. Water's neutral. The whole thing has a +3 charge, and so this is iron 3. Iron 0 is D8. So iron 3 plus has lost 3 electrons, so it's D5 electron configuration. And then I tell you that it's high spin, so high spin D5. 1, 2, 3, 4, 5. Okay, so now let's do our crystal field stabilization energy. It's equal to 3 times minus 2/5 delta oct plus 2 times plus 3/5 delta oct. Well, 3 times minus 2 is minus 6, and 2 times plus 3 is plus 6. So this crystal field stabilization energy for this ends up being 0. Okay, so this is no more stable in the crystal field than it is as the free ion. All right, let's look at this one. So this, again, these are all waters, and so this is chromium 3. And chromium 0 is a D6 system. So then if it loses 3 electrons, it must be a D3 system. So now let's populate our orbitals again. I tell you that this is high spin, but it's in the problem, but it's really not. High spin or low spin is not a thing here. I just didn't want to give that away. In the problem, it'd be like this on a quiz or exam. So there's only 3, so high spin's not really a thing here. If there was a fourth, if this was chromium 2, then the fourth electron would go up since it's high spin. So now the crystal field stabilization energy is equal to 3 times minus 2/5 delta oct. So it's equal to minus 6/5 delta oct. So that's the stabilization that this complex feels when the 6 waters come around and coordinate to it. The stabilization that the metal center feels. All right, and another +3 metal, so this is cobalt 3. Cobalt 0 is D9, so cobalt, if it loses 3 d electrons, must be D6. And in the problem, I'll let you know that it's high spin. So now high spin is actually going to matter. 1, 2, 3, 4, 5, 6. Crystal field stabilization energy is equal to 4 times minus 2/5 delta oct plus 2 times plus 3/5 delta oct. So this is minus 8 minus 8/5 delta oct plus 6/5 delta oct, or 6 minus 8 gives us minus 2/5 delta oct. So the crystal field stabilization energy in this case is minus 2/5 delta oct.